Hey everyone, this is my second video in my quantum series. Today I'm going to talk about the photoelectric effect and how that proved light was a wave. Light was a particle. So before we fully explore the photoelectric effect, I'm going to talk about what scientists before thought light was. So initially, scientists before the photoelectric effect was observed, they thought light was just an electromagnetic wave. So they thought the energy of light was only dependent on its intensity. Now we know that the energy of light is dependent on its frequency because the energy of a photon is described by this equation below, where h is Planck's constant. And so we know that energy of light is therefore dependent on frequency, but they didn't know this. And this explains why scientists thought the conclusions that they drew from the photoelectric effect was very absurd and confusing. Okay, so let me just explain the photoelectric effect really quick and what kind of experiments came along with it. So what happened was scientists would shine light of known velocity, known frequency, known wavelength, known intensity onto a photosurface. A photosurface is just a metal sheet, and whenever light was incident on this photosurface, it would transfer its own energy into the electron. And some of the energy was used as work done to overcome the electric attractive forces between the electrons and the positively charged metal ions. And the remaining energy that was transferred from the light to the electrons was used as kinetic energy, converted into kinetic energy of the electrons. And that's why we see the electrons being ejected out of the photosurface and being collected onto the collecting plate. Scientists would also change the variable voltage, the voltage of the variable voltage cell over here. And this would change the potential difference between the photosurface and the collecting plate. And that would change the way in which electrons moved. Sometimes when high variable voltage was used, when they set the variable voltage cells at a very high, not very high, but like a somewhat high voltage, then the electrons would be collected onto the collecting plate and they would flow through the circuit, generating a current. And the current was measured by this ammeter over here. So what scientists did was they varied the voltage of the variable voltage cell, and which effectively changes the voltage between the photosurface and the collecting plate. And they checked how the current changed. So as we expect, at very high voltages, the collecting plate would be positively charged, attracting electrons, and therefore the current would be very high. And as we reduce the voltage, make it less and less positive, the collecting plate would be less and less positively charged, and it would attract electrons to a lesser extent, resulting in lower current. And so current decreases. That's what we probably expect, right? And there comes a point within of the voltage where the current equals to zero. We call that the stopping voltage. And current is equal to zero because variable voltage is just about negative enough so that all of the electrons' initial kinetic energy is used as work done against this electric force of repulsion between the negatively charged electrons and now the negatively charged collecting plates. So the electrons, they lose all their kinetic energy and their velocity becomes zero at this like very small, infinitesimally small distance away from the collecting plate. Therefore, there's no current. And as the voltage of the collecting plate becomes more and more negative, electrons are going to be even more repelled, which means that current is bound to be zero. So the scientists found that the relationship between voltage and current within this experiment was something like this. Straight line until the stopping voltage, a straight line. And then after that it goes up. And from this experiment, and also scientists did this experiment. One thing worth mentioning is that you can use the stopping voltage to calculate the the kinetic energy of the electrons. The kinetic energy of the electrons was calculated as the charge of electrons times the voltage of the variable voltage cell, and at the stopping voltage. I'm going to call this Vs. So kinetic energy of the electrons is the charge of electron times the stopping voltage. This is according to the laws of conservation, because all the kinetic energy has to be converted into, all the kinetic energy is used as converted into work done against the electric repulsive force. If I had to go into detail, it would be like initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. That's just the conservation of energy. Initially, let's call this, the initial kinetic energy is KEE, and at the start, let's say the potential difference is 0 because the photo surface is too far away from the collecting plate, and at the final and kinetic energy final would be 0, because this final moment that we're talking about is when the electron just stops at an infinitesimally small distance away from the collecting plate. So kinetic energy final is 0, and the electric potential energy would be calculated by charge times electric potential, and charge is E. Okay, hopefully that makes sense. And from this experiment, there were 4 very interesting observations that scientists found very absurd and that questioned how they viewed light. And it's very important that you understand these 4 interesting and absurd observations. Firstly, it was that the intensity of incident light does not affect energy of emitted electrons. This is one of the 4 conclusions that the scientists came up with that really baffled them. And how they found this conclusion was on the graph, right? We got current, got voltage, and this is the graph for a very very high intensity light. And this is also the graph for a low intensity light. And so we see that for both intensities of light, stopping voltage is the same. And because of this equation that we established here, we know that the kinetic energy of the electron initially, when it's first ejected out of the photosurface, is determined by the stopping voltage. So because the stopping voltage remains the same for both intensities, whether it's high or low, this means that the intensity of light does not affect the energy of the kinetic energy of the electrons emitted in any sort of way, which means that the energy of light isn't determined by the intensity, which is really baffling to scientists at first, because they thought that the energy of the light was dependent on the intensity of light. And the second observation that they made is that the electron kinetic energy depends on the frequency of the incident light. And how they found out about this was they plotted another graph, voltage graph. And I'm going to draw a graph for a high voltage light. A high frequency light. One for a low frequency light. Here, you can see their stopping voltages are different. Matter of fact, the stopping voltage of the absolute value of the stopping voltage of the light with low frequency is lower, and this means that the kinetic energy of the ejected electron is lower if the frequency of the incident light is lower. So again, just like the reason I mentioned before, scientists were really baffled by this because they didn't, in their equation for calculating the energy of light, they didn't have frequency, and they didn't have frequency in that equation. So they were just really confused where this frequency came from. And another surprising observation they made was that below a certain minimum frequency, no electron was ejected. Now, the graph that proves this is a little bit different from the first two I mentioned because the axes are frequency and kinetic energy. So let's say we have photosurface 1. Photosurface 1. And we call the frequency at which kinetic energy is 0, kinetic energy of the emitted electron is 0. I mean the maximum frequency where the kinetic energy of the ejected electron is 0 as the threshold frequency. And for photosurface 2, let's say the graph is like this. This is threshold frequency number 2. And we can tell that although both photosurfaces have different threshold frequencies, we can tell that both photosurfaces, they do have this, below this each respective threshold frequency, no electron was ejected. We can tell that because kinetic energy of the electron is 0 here. And once again, this was really confusing to scientists because they thought, okay, let's say somehow our equation for calculating energy of light was wrong and frequency was somehow involved. But they just thought that even if at a certain very low frequency there wasn't enough energy of light to eject electrons, if they increase the intensity of light, then the energy of light would increase and therefore some electron would be ejected. In theory, light in any frequency should be able to eject electrons as long as there is enough intensity. But obviously this wasn't the case because no matter how much they increase the intensity of light, if the light's frequency was below the threshold frequency, nothing would happen. And also, the fourth surprising point that they found out was electrons are emitted with no time delay. So initially, what scientists thought was possible was that even if the waves, they don't have waves, like each one sort of like hit of the wave, even if they didn't have enough energy to eject electrons, after a certain amount of time, the energy transfer from the wave onto the electrons would just keep on accumulating and accumulating and accumulating until the electron is energetic enough to be ejected. But obviously, that wasn't the case here, because electrons were emitted with no time delay. And with this wave theory about light, electrons should be emitted with time delay, especially at low intensities of light. And about these very interesting and absurd conclusions that couldn't be explained with the classical model of light, Einstein came up with a justification. And this will be explored in the next video.